Hi everyone. So today we're going to learn about molar mass and percent composition, okay? Before we get started, you guys are going to need a few materials. So you're going to want your mole map, okay? Mine's orange, yours is blue, it's okay, same stuff. You're going to want a periodic table, just like this one, right? And you're going to want your worksheet, okay, that I handed out. Mine is filled out, okay? Yours will be after Friday. Okay, so the last time that we talked, right, we talked about the mole. Okay, so we learned that 1 mole is equal to 6.02 times 10 to the 23rd particles. Okay, so really it could be any units that you want, right? So it could be 1 mole of atoms, or 1 mole of molecules, 1 mole of ions, 1 mole of marbles, dollar bills, whatever you want to count, okay? You use it just like you would use a dozen, right? A dozen doesn't have any units, but when you talk about a dozen chairs or a dozen people, then you have units. So it's the same thing with the mole. Okay, and we know that when we make an equivalent statement like this, right, then there are two different ways that we can represent that as a ratio, right? So we know that we can say there's 1 mole for every 6.02 times 10 to the 23rd particles, right? Or we can also say that there are 6.02 times 10 to the 23rd particles in every 1 mole, okay? So when you guys are doing those calculations on your worksheet, you're going to want to figure out which one of these ratios you want to use. And that's where your mole map comes in. Okay, so if you take a look at your mole map, right, so you have your mole here, okay, in the center. And let's say that you would like to go to representative particles, okay, this way. So you want to go up here to particles. Okay, so in order to get there, then you're going to want to use this conversion factor, right? Because that's going to help you convert between particles and moles. But if you want to go back from particles back to moles, okay? Oh, I'm sorry, so this one is going to help you go from moles to particles, right? And if you want to go back from particles to moles, okay, you want to use the one that has 1 mole for every 6.02 times 10 to the 23rd particles. All right? So this part we kind of already know, but what we don't know is how to go from moles to mass and from mass to moles. So that's what molar mass is going to help us do. All right. So, and by the way, guys, I realize that the drawings and the things that I'm writing on the board are in mirror image for you. So hopefully you can follow what I'm saying and follow the mole map and the other resources that you have there. Okay. Okay. So I'm going to erase this. Okay, and I'm going to remind you guys of what we talked about in our last class. So we showed, right, that 12.01 grams of carbon contains 1 mole of carbon atoms. Okay, if you're not sure about that, go back and look at your notes. Remember, we did those calculations, right? And we said this is going to be true for any element, that its mass in when it's the same as the the atomic weight in AMU, right, except that it's expressed in grams, that's going to be 1 mole of that particular atom. Okay, so we know that 12.01 grams of carbon is equal to 1 mole of carbon atoms. So we could also make an equivalent statement here, right? We could say that 12.01 grams of carbon, there are 12.01 grams for every 1 mole, or we could say that there's 1 mole of carbon for every 12.01 grams. Okay, so we have our two ratios here, right? All right, so that is the molar mass, right? We've just defined for ourselves a vocab word. So molar mass, okay, just means the mass of 1 mole of carbon atoms, okay? Or the mass of 1 mole of any type of element, okay? All right. So let's do a practice problem to see how we might actually use these ratios. All right, so pull out your handy dandy worksheet, okay? I'm looking at number 7, okay, under the mass to atoms or atoms to mass section. Okay, so number 7 asks, what is the mass of 6.99 times 10 to the 23rd atoms of potassium. All right, so this time we're not working with carbon, we're working with potassium, okay, but the idea is the same. So we have 6.99 times 10 to the 23rd atoms, okay, and we want to know what that mass is. So we need something to take us from atoms all the way to mass, okay? So first let's convert to the mole, because if we look at our mole map, all right, we are up here in representative particles. We would like to go down here to mass. So we are going to do that via the mole, okay? All right, so we know that there's 1 mole of potassium for every 6.02 times 10 to the 23rd potassium atoms, right? Okay, and we also just learned that we can convert from moles to mass using the molar mass, okay? So you look on your handy-dandy periodic table, okay? We find potassium, which is over here in group 1, and we look and we see that the molar mass of potassium is 39.10 grams per mole. Okay, so we just plug that into our calculation here. So we have 39 point, oh, did I write that down wrong? Nope, sorry, it's 10, so 39.10, okay, grams for every 1 mole of potassium, okay? So here we started off in particles, right? Then we converted from particles to moles using our mole ratio that we already learned, okay? Then we went one step further and we converted to mass using the molar mass, which is the new concept that we just learned today. Okay, so if you do this math, then you should get 45.4 grams of potassium, okay? That is the weight of 6.99 times 10 to the 23rd atoms of potassium, okay? And we want to check and make sure that we have the right number of significant figures. So we started off with 3 significant figures here, so we should only have 3 in our answer. Okay, so we're looking pretty good. All right, so, okay. All right, so we've learned about the molar mass of a particular element, right? All you do to find the molar mass is look on the periodic table. Let's say I wanted to do sodium. Okay, I look and I find sodium and I see the number 22.99 written there. So that's both the mass of an average sodium atom, but it's also the molecular mass, the molar mass. It's the mass of 1 mole of sodium atoms in grams, okay? So that's how you find the molar mass of a single element. It's pretty simple, right? But we can expand what we've just learned to compounds. So let's see how we would find the molar mass of an entire compound. Okay, how about carbon dioxide? All right. So I'm going to tell you that 1 mole of CO2 or carbon dioxide, okay, weighs 44.01 grams. Okay, we just learned that when 1 mole of something has a certain weight, that is its molar mass, right? So we could say that the molar mass of CO2 is 44.01 grams per mole, okay? All right, but how did we get there? Because I just sort of gave you that number, so how do we know that's correct? Okay, well, let's think of what carbon dioxide is made up of, right? So CO2 consists of 1 carbon atom, right? 1 molecule of CO2 has 1 carbon atom and 2 oxygen atoms, right? Okay, well, we know the molar mass of carbon, right? We can look on our periodic table, and we've already calculated it, right? We know that it's 12.01 grams per mole, okay? All right, and we also know that the molar mass of oxygen, we can look again on our periodic table, is 16 grams per mole. But I have 2 of them, right? So for every carbon dioxide molecule, I have 2 atoms of oxygen, which also means that for every 1 mole of CO2, I'm going to have 2 moles of oxygen, right? Okay, so 2 times 16.00 grams per mole is 32.00 grams per mole. Okay, so all I do to find the molar mass of this entire compound is to add up the molar mass of its parts. So 12.01 grams per mole from the carbon and 32.00 grams per mole from both oxygen atoms. So if I add these up, okay, I'm going to get, let me just make sure I give you the right number. Yeah, so I'm going to get 44.01 grams per mole, right, which is the answer that I gave you initially. Okay, so, all right, so if that went a little fast for you, let's just back up for a second, right? So in one CO2 molecule, there's one carbon atom and two oxygen atoms, right? What if I had a dozen CO2 molecules, so 12 CO2 molecules? How many carbons would I have? How many oxygens would I have? So I hope that you would say we would have 12 carbons, right, and 24 oxygens. Okay, so now let's just say instead of having a dozen, right, we're going to have a mole of CO2 molecules, okay? So if I have a mole of CO2 molecules, how many carbon atoms do I have? Hope you would say a mole, right? And then if I have a mole of CO2, how many oxygen atoms would I have? So again, in every 1 mole of CO2, we got to have 2 moles of oxygen, okay? All right, so we got ourselves to the molar mass of a compound, right? Just by adding up the molar mass of its parts. So why don't you guys give this a shot? So why don't you guys try to figure out the molar mass of ammonia? So the molecular formula for ammonia, okay, is NH3. So why don't you pause the video, go ahead and try and figure that out. Okay, so I hope you guys gave this a good shot. So let's look at how to do this. So ammonia is NH3, right? It has 1 nitrogen atom. If you look on your periodic table, you'll see that the molar mass is 14.01 grams per mole, okay? And you're going to have 3 hydrogen atoms, right? So the molar mass of hydrogen is the molar mass of hydrogen is 1.008 grams per mole. So we need 3 times that much because we have 3 hydrogens. Right? So don't just think of it as atoms, okay? It's the ratio. So for 1 mole of ammonia, there's 1 mole of nitrogen and 3 moles of hydrogen. So that's where we're getting these numbers, okay? So if we were to do this math and add them up, hopefully you should have gotten 17.01 grams per mole as the molar mass of ammonia. So there's a couple more practice problems on your worksheet, so you can give those a shot. Okay. So the last thing we need to talk about is percent composition. So often it's helpful to understand what percentage of the mass of a compound comes from a particular element, especially when you've just discovered some new compound. So let's say you were out in the rainforest in South America and you discovered some, miraculous new drug, but you have no idea what it is. Well, if you can figure out how much of the weight comes from, say, carbon, hydrogen, oxygen, nitrogen, whatever's in your compound, then you have a much better chance of figuring out what your compound is. Okay, so we're going to learn a little bit about percent composition. All right, so the technical definition for percent composition is that it is the mass of an element in 1 mole of a compound. Okay, so the mass of the element in 1 mole of a compound, all right, divided by the mass of 1 mole of the entire compound. Okay, and then I'm running out of room, but all of this times 100%. Okay, sorry to squish that in. So the ratio that you have is the mass of the element in 1 mole of the compound, right, divided by the mass of 1 mole of the compound. So let's do an example so this is clear, okay? Let's come back to our carbon dioxide, CO2. Okay, so in 1 mole of CO2, how many carbon atoms do we have? I hope you say 1 mole. Okay, so if we have 1 mole of carbon atoms, what does that weigh? So we've already talked about that, right? Again, you can look on your periodic table, look at carbon, you'll see that the molar mass for carbon is 12.01 grams per mole, right? What was the molar mass of CO2, the entire compound? It was 44.01 grams per mole, right? So I'm looking for how much of this 44.01 grams comes from carbon. What percentage comes from carbon? Okay, so to find that, I just take 12.0, okay, let me set this up a little better. So I have the percent composition of carbon is going to be 12.01 grams, okay, which is the mass of the element in 1 mole, right? So 12.01 grams per mole becomes now just 12.01 grams, okay, divided by the mass of 1 mole of the compound. So the mass of 1 mole of CO2 is 44.01 grams. Okay, 0.01 grams. And then this whole thing needs to be multiplied by 100% in order to make it a percentage, okay? And if we do that math, we should get 27.29%. So that is how much of the weight for a CO2, a mole of CO2 is going to come from carbon, okay? We can also do the oxygen. So let me erase this. Okay, so for the oxygen, so the percent composition of oxygen is going to be, now this time we have to account for the fact that there are 2 oxygens in every CO2 molecule, right? So the mass is not just going to be 16 grams per mole, it's going to be 2 times 16 grams per mole. Okay, so that is 32, and then that is divided by 44.01 grams per mole, and then all of this times 100% to make it into a percentage, okay? And that should give us 72.71%. Okay, so that is the mass percent of oxygen in CO2. Okay, so if you guys want to try this yourself, you can see if you can figure out the mass percentage of nitrogen and hydrogen in the ammonia that we just talked about. All right. Okay, guys, so that's all I have for you on molar mass and percent composition, okay? So give those worksheets a shot. So again, you should have 3 worksheets complete, right? They were all stapled together for you. The 6.1, 6.2, and then all those practice problems, okay? And you should also, so your homework for tonight is going to be reading journal notes for chapter 6.3, okay? And when I say tonight, I mean day 5, which for most of you is Friday, okay? So by the time I see you guys again on Monday or Tuesday, I expect to see from you the worksheet packet, right, and the reading journal notes for 6.3, and the section review questions from 6.1 and 6.2, okay? Hope this was helpful, and I'll see you guys on Monday.